Okay, I am now recording, and we have people sitting here, and I think we are good to go. And first of all, I would like to introduce today's presenter is Dr. Morteza Sadeghi. He is working at California's Department of Water Resources, and as mentioned in the emails, we are going to talk about a model based on hyperspectral data and how it is, and the workflow which connects this model to satellite imagery to estimate soil moisture. So I think it's better if we go straight to the presentation, and we are all ears.
Yeah, do you hear me?
Yes, clearly.
Okay, thanks, Ali, for inviting me to this presentation. I appreciate this opportunity to talk about some of my recent studies. It's a great pleasure to be with you today. And I hope we have a good discussion as well at the end of my talk. So as you mentioned, today I'm going to talk about the optical trapezoid model, or OPTRAM, for mapping soil moisture at larger scales using satellite data. So the initial idea of OPTRAM was developed at the laboratory. So that's why today I'm going to talk about the story, how this model was developed, how we started from the idea in the lab, and how we expanded the idea to the large scale. So first of all, the question is why soil moisture? Why is it important to monitor, measure, model soil moisture? So soil moisture is a critical state variable, important in several disciplines of earth science. For example, the coupling between water, energy, and carbon cycles is largely dependent on soil moisture. From the agricultural standpoint, we need to monitor and manage soil moisture for crop production, because this is the primary source of water for crop use. And also the partitioning of land surface water fluxes, for example, an infiltration, a precipitation event partition into runoff and infiltration depends on the soil moisture. And also soil moisture controls the ecosystem diversity and function. So for many reasons, we need to have accurate data of soil moisture content at a variety of scale, from field scale up to the global scale. We know that we can measure soil moisture using traditional gravimetric methods and also using in situ ground sensors. But these measurements will be costly, especially if we want to cover a larger scale. So that's why we are interested in remote sensing of soil moisture, especially using satellite data. And fortunately, we have a great correlation between soil moisture and the soil electromagnetic radiation at several bands. So the microwave band, especially the L band, is the most promising current method for mapping soil moisture on a global scale, because it's not impacted by clouds, it has good penetration depths, so it can penetrate through the canopy and see good amount of soil underneath the canopy. The major limitation for local studies is its resolution. So it's more appropriate for global scale because the microwave data provide us relatively low resolution. So that's why we are also interested in optical remote sensing approaches for soil moisture mapping, because optical data, they can provide much higher spatial resolution. So they are limited in penetration depth. For example, if you have a cloudy sky, we cannot use optical data, but whenever they are available, they can produce high resolution data. So yeah, for today's talk, I'm going to focus on the optical remote sensing of soil moisture. Basically, a few years back, I was interested to know the physics behind soil darkening, why soil looks darker when wet, so like many other materials. And this can generally be explained by the reflectance of the soil and optical properties of the soil, because water molecules are strong absorbers of light, and that's why when we have higher soil moisture content, the soil reflectance will be generally decreased and soil looks darker. And that's how we can sense soil moisture remotely from optical data. To explore the relationship between soil moisture and soil reflectance, a few years ago, I found this radiative transfer model very helpful. It's called the Kubelka-Monk two-flux model, and it explains the radiative transfer in soil and other materials by two vertical fluxes. I is a forward light flux and J is a backward light flux. And as they go through the layer, they can be partly absorbed, which is proportional to the absorption coefficient of the layer K, and can be partially scattered, which is proportional to the scattering coefficient of the layer S. And the scattering light will contribute to the backward flux J, and eventually it will go out of the soil or the material and will form the soil reflectance. So by solving these two ordinary differential equations that can mathematically explain the Kubelka-Monk two-flux model, I got this very simple yet physically based model between soil moisture and soil reflectance. So in this slide, you see the capital R is soil reflectance that can be measured from the sensor. And using this equation, the small r that we call transform reflectance, if we transform the capital R, like 1 minus r squared over 2r, so we call it transform reflectance. And we showed that there is a linear relationship at the SWIR or shortwave infrared wavelengths between soil moisture and the transform reflectance. So in other words, so we know that the reflectance has an inverse nonlinear relationship with soil moisture. So we already know that from the measurements. But this model proposes that if we transform the reflectance into the transform reflectance, the small r, then we would expect a linear relationship between soil moisture and transform reflectance. So this linear physically based model helped us a lot in our calculations of soil moisture, or converting the reflectance map at the SWIR band to a soil moisture map. Because the model is linear, we do not need any site-specific calibration parameters, and it's a scaling relationship, so we can scale a map of soil reflectance into soil moisture content. So we initially tested this idea in laboratory using an AST spectral radiometer operating at the 400 to 2500 nanometer domain, and we measure reflectance spectra of various soil samples from Arizona, covering a wide range of soil texture from sandy soil up to the clay soil with different mineralogies and colors, and as you see in this slide, as they are apparent from their color. And we measured reflectance spectra at different moisture levels. So here I'm showing an example of the measured reflectance spectra for one of the soils. And I'm showing each spectra for a moisture content level. And as you see, in most of the wavelengths, soil reflectance is decreasing by increasing the soil moisture content. And this is what we already know from previous studies. And if we look at the data, for example, I'm here showing data at two SWIR wavelengths, 1650 nanometer and 2210 nanometer. And you see that reflectance is inversely correlated to soil water content, and the relationship is pretty much nonlinear. However, if I transform the reflectance into the transform reflectance based on the Kubel-Command model, so we see the relationship turns into more a linear relationship, especially at the 2210 nanometer wavelengths. So this data primarily proves the adequacy of the proposed linear physically based model. And it was a proof of concept for us. So we did more laboratory experiments, this time using a shortwave infrared camera, as you see in this picture. So we had an experimental setup like this. We had a soil column with a coarse Hilsha cell. So the column was at almost 100% transparent. So we could image the soil from the shortwave infrared camera. And so we conducted an upward flow experiment. So we wetted the soil from the bottom, and then we were imaging the soil column during the experiment using the camera. So in this slide, I'm showing results of the camera imaging for various times during the flow experiment. And it's one example for one of the soil, AZ7, which was a sandy loam soil. And using these images, And also the proposed linear physically based model, it could scale the optical data into soil moisture data with a very high spatial resolution. For example, here 0.1 millimeter and high temporal resolution 1 minute here. So in the right plot, you see soil moisture profiles at different times coming out of this this methodology based on soil camera imaging, and also the linear scaling. And here I'm showing the results for different soils, and I'm comparing the soil moisture estimates based on the soil camera, which is the blue line. And we also had a TDR sensor as an in situ measurement in the soil column as a reference, which is showing by the red dots. And as you see, we have a pretty much good agreement between the camera and the TDR data for mapping or monitoring the soil moisture profile during the flow experiment. So giving us more confidence about the adequacy of the linear physically based model. So after all these laboratory experiments, one day I was reading through ResearchGate, and I faced an interesting question. And the question was, is there any method to map soil moisture using Sentinel-2 satellite data? So as you know, Sentinel-2 is a European Space Agency satellite launched in June 2015 with a spatial resolution of 10 to 60 meter, temporal resolution of about 5 days. And it has 13 optical bands in visible NIR and SWIR, but it does not have any thermal band. And the question was interesting because back then, most of the remote sensing methods applied to similar satellites like Landsat, they were using temperature data or the thermal bands. And because Sentinel-2 did not have any thermal bands, so basically many of those traditional methods could not be used for Sentinel-2. So there was basically no method for turning the Sentinel-2 data into a soil moisture map. So that was the beginning, and it gave us the idea to develop a large-scale optical method for soil moisture mapping that we later called optical trapezoid model, or OPTRAM. And we call it trapezoid model because we got the idea from the traditional trapezoid model, which is based on the assumption that there is a linear relationship between soil moisture and land surface temperature. So basically, in this method, if we have a satellite image and if we plot land surface temperature versus a vegetation index such as NDVI, it commonly forms a trapezoidal space. And if we fit lines to the edges of the trapezoid, so that the top edge would be the dry edge, because the higher the higher the land surface temperature, the lower the soil moisture. There is an inverse relationship. And the bottom line will be the wet edge. And in this method, it is assumed that the soil wetness W is proportional to the distance D1 for each pixel, which is one of the dots for each pixel. So it's the distance from the dry edge over the distance from the dry edge to the wet edge, D2. So D1 over D2 is assumed to be a measure of soil wetness. So similarly, in the optical trapezoid model, we assume the relationship between sphere transform reflectance, or STR, and a vegetation index such as NDVI, because we already showed in the lab that there is a linear relationship between soil moisture and STR. So we could replace this linear relationship in the thermal or traditional trapezoid model. So in this trapezoidal domain, if we fit lines to the edges of the trapezoid, the upper edge would be the wet edge, because the higher the soil moisture, the higher the transform reflectance. And the bottom edge would be the dry edge. And similarly, the soil wetness will be estimated as the distance D1 over distance D2 at each given vegetation index level. So in terms of the mathematical formulation, so we already showed that there is a linear relationship between soil moisture and STR in the lab. And if we assume there are the edges of the trapezoid are also linear, and we combine these relationships, we get the final OPTRAM formulation, as you see in this slide. So in the OPTRAM formulation, we have W soil wetness, which can be calculated as a function of NDVI, and STR, which is the sphere transform reflectance. So purely using optical data, so we have NDVI from red and NIR data, we have STR from the sphere band. So using only optical data, we can estimate the soil moisture content. And we have 4 parameters in this model. ID and SD are the intercept and slope of the dry edge, and IW, SW are the intercept and slope of the wet edge. And for using OPTRAM, we need to find these parameters first. So for calibrating the OPTRAM, we propose plotting STR versus a vegetation index such as NDVI or fractional vegetation cover or any other vegetation index. Then we have a trapezoidal space like this, and we propose 2 methods for determining these edges, or basically getting the OPTRAM parameters for each area. So the first approach is just a simple approach, visually fitting lines to the densest part of the data cloud, as you see here. And also we always have the option to use actual soil moisture data if available for least square calibration of the OPTRAM parameters. So we initially evaluated the OPTRAM model for 2 watersheds in the United States, the Walnut Gulch watershed in Arizona and Little Washita watershed in Oklahoma. And we showed that OPTRAM yields reasonable estimates of soil moisture when compared to the in situ soil moisture data. And we published the first OPTRAM paper in 2017. And after that, fortunately, many people all around the world, they found it useful for their research, and they employed the model and used for mapping soil moisture for their own research project. And it was interesting that a variety of sensors were used in these studies. Different sensors at different spatial resolution, from MODIS with 1 kilometer resolution data to Landsat with 30 meter resolution, to Sentinel-2 with 10 meter resolution, and also the OPTRAM was used for field scale applications with much higher resolution field scanners, about a millimeter scale resolution field scanners for mapping soil moisture at very high resolution at the field scale. So it was a good news to see OPTRAM is doing good. Of course, accuracy depends on the conditions of the land and vegetation. So we saw a range of accuracies from very accurate estimates to not that great estimates of the model. But in any case, it could be useful in filling the gap for using optical remote sensing data for mapping soil moisture. So that was a brief story about how OPTRAM was developed from our initial studies in the lab, and then expansion to the watershed scale and larger scale. So here I'm showing a few publications out of these series of studies. So 2015 paper in remote sensing of environment is about the derivation of the linear physically based model between soil moisture and transform reflectance. 2017 in Veduson journal is about the column experiment in the lab using the SWIR camera. And the 2017 in remote sensing environment this is the first paper that we introduced the OPTRAM approach. So if anybody has interest in about the details of these studies, so you can take a look at these papers, and I'll be happy to get, if you want to shoot me an email and ask and discuss different aspects of the OPTRAM model. And yeah, I'll stop here. I'll be happy to take any question or comments. And again, I thank you so much for your time and attention.
Thank you very much. And thank you very much. It was very interesting for me, and of course, hopefully for our audiences here. And I have many questions, but I would like to first ask our audiences here, either online or sitting here, to share the questions, and we would be happy to have them.
Of course.
Yeah, thanks a lot for this interesting talk. It's a topic fairly new to me, especially also this water sensing, as well as working with satellite. I am always wondering, because you also mentioned that I think a general problem with the soil sensing, maybe in general remote soil sensing, is the penetration depth. And then I also saw the revisiting time of 5 days, and I was somehow wondering if with this application you might also kind of underestimate or overestimate the soil water content, at least in lower soil depths than few centimeters.
Well, yeah, that's a very good question. Because as you mentioned, optical data, especially for bare soil, they just see the soil very surface, just 0 centimeter. and what we have in like ground sensors, or what we need for a lot of our applications, are like top 2 inches for surface soil moisture and then root zone soil moisture. And of course, if you want to use optical data for estimating near surface soil moisture, there would be a bias or like a drying bias, unless we kind of calibrate the model using in situ data. But one promising thing for OPTRAM is that when we have vegetation, we assume that there is a linear relationship, or there is at least a large correlation between soil moisture and vegetation water content. And then the sensors are seeing the vegetation, so they can sense basically the vegetation water content. And then if we assume there is a correlation between vegetation water content and soil moisture in the root zone and like in deeper than the surface, then we would expect to at least get some sense of more deeper soil moisture. Yeah, but in any case, this is an inherent limitation of the optical remote sensing, especially for bare soil.
Yeah. I think this is also maybe one point, because as I said, it's quite new to me. One point maybe I didn't completely understand where you showed this relationship of NDVI and soil moisture, because I can imagine that this relationship is highly dependent on the vegetation present, but I guess you have to somehow calibrate for this kind of effects, or
yeah. So yeah, are you talking about this slide in the lab or later in the larger scale?
no, sorry, this trapezoid, I think a few slides forward. Yes, yeah, exactly.
Maybe this one.
Yes, this one or the one before with the, or maybe because the one with the temperature I might understand a little bit better, the one with temperature and the NDVI. Yeah, exactly.
Oh, okay.
So because I could imagine that yeah, I could imagine that this relationship of vegetation index and temperature is highly dependent on the vegetation type present. Yes, or not much maybe.
Yeah, you are right. You are right. So of course, these like trapezoid, like if we restrict the area, we would, like, based on the soil type, based on the vegetation type, based on the land conditions, we would hopefully get more and more accurate estimates. I mean, like, it's a matter of like the computational and all the computational demands. So for our initial study, we just considered the whole watershed, put together all the data for all soil, all vegetations, and we had just one OPTRAM model for the whole watershed, and that's why we had,
May I quickly ask maybe a stupid question? I tried to Google before, but what exactly is a watershed? Sorry.
Watershed is so it's like basic hydrology, so it's a boundary that for that you have a converging river system, so it can collect infiltration, and based on one main river system, so you can define a watershed. But yeah, you're right. So these definitions are not always accurate, so because these watersheds can commute. But anyway, yeah, so we see these scatterings here. This is because what you mentioned about the vegetation type and soil type and all the land conditions. So I never studied, like, dividing this large area into much smaller areas based on vegetation class or soil class, and then have one OPTRAM model for each class. So I would expect more accurate estimates in that case, but it's going to be much more computational demands. So
you would somehow need to segment the different areas, or
yeah,
somehow calibrate individually, or
yeah, this is what I expect. If for example, for each vegetation type, we have a segment, and then we have a specific calibration for that segment. So hopefully we get rid of some of these scatterings. But we applied the model for the whole watershed, and we got reasonable estimates, about 4 or 5% soil moisture accuracy. For the Walnut Gulch, you see much more scattering. So probably we could get better estimates here by classification. Little Washita here was okay, because probably it was a more uniform watershed compared to the Walnut Gulch in Arizona. But yeah, that's a good topic of research.
To go from one kind of one measurement and then deduce on the other one, and
sorry, I'm not sure if I understand you correctly.
No, I was just saying that I admire the work, and also to combine this different kind of measurements and kind of build up on them is a very interesting approach. Yes, thanks a lot.
Yeah, thank you.
I myself would like to initiate and ask a small question. I was always thinking about this model, and I was thinking that is it possible to do the same workflow for organic matter? Because organic matter has a smaller effect on soil reflectance, but anyway, regardless of that, is it possible to apply this kind of workflow on soil organic matter and have it measured in laboratory, and then overgeneralize it to satellite or maybe UAV data?
That's a good question, but I imagine organic matter is much more challenging than the soil moisture, because the signal is just weaker compared to soil moisture. So when you change soil moisture from dry to saturated, you will have a large change of reflectance. And in lab, so this is for one soil you study. So you can have one soil with the constant background, like constant texture, organic matter, everything constant, and you can change soil moisture at the same time. So soil moisture is a state variable, so it can change in time. So that's why we can, the background is constant, and what is changing is the soil moisture, so changing the signal. But the challenge with organic matter is that the organic matter is a constant or almost constant soil property. So, and what you can study is different soils. So you have different soils with different level of organic matters. Of course, you see a correlation between organic matter and reflectance in different soils. But the problem is that you also have other factors changing between soils, like you have texture changing, soil color changing, soil roughness changing, and if you study just dry soil, so just isolate the soil moisture, and that's gonna add another uncertainty at large scale, because you always have changing soil moisture content at large scale. But in the lab, you would see a correlation between organic matter and soil reflectance, but the isolating only the soil organic matter effect on reflectance is a really challenging task.
Yeah.
Because you need to know how other factors, like as I mentioned, soil texture. So you have a sandy soil with low organic matter, and you have a clay soil with high organic matter, for example. So you have, besides the organic matter effect, you also have texture effect, color effect. So those are changing the soil reflectance as well. So short answer is, it might be possible, but it's much more challenging than soil moisture.
Isn't it possible to, for example, have just one type of soil and change for example, fertilize it synthetically?
Maybe. Yeah. Of course, we can like mix one background soil with different organic matter content. And in that case, we have a controlled experiment to study the effect of organic matter on reflectance. And of course, we can see the effect, but when we are going to apply this method in real world, then we do not have such a thing. Like, we do not have one soil with different levels of organic matter. So everywhere organic matter is changing, soil is changing,
Thank you very much. Any other questions from the speaker? Okay, seems like we have no other questions, and we would like to thank you for presenting the workflow from laboratory to space. I myself really enjoyed it, and it was really interesting for me to see how it worked, especially with that image changing of the soil moisture. And we would like to thank you again for giving a speech, and that's it for our Duna seminar.
Thanks, Ali, again for inviting me, and thanks everyone for your time joining this presentation. It was a great time presenting my work and getting your feedback. So I hope I could attend in person, but it's very far from me. So hopefully one day I can attend in your university and give a talk in person. Yeah, thank you so much. And again, if everyone has any questions later, so you can email me. I'll be happy to provide details about the OPTRAM model or other relevant work we did in the past several years. Yeah, thank you so much. Have a good day, everyone.
Bye.
Thank you. Bye-bye.
Bye.